Welcome back, dear students. So, already in the first session, we have discussed the basic mechanism of anaerobic digestion, different stages of anaerobic digestion, and types of digesters, their classification, and their relative merits and demerits, etc. So, in this session, we will mainly discuss the design of a digester, that is, how to select the size of a digester based on our requirement, and some applications of anaerobic digestions, etc. So digester volume, this is the digester, a typical block diagram of a digester. We can classify this into 4 volumes. First one is collection volume, where the gas is to be collected and to be circulated outside through the collection pipe. That is a small volume, that is known as collection volume. The pipe connection, etc., will come in that volume, through which this gas will be taken outside. Then we have a gas storage volume, VGST, which is a temporary storage of biogas. Then VD is the active digestion volume. So that is the volume where this digestion takes place, anaerobic digestion. And at the bottom we have VSL, which is the sludge layer volume. So we know that the another output of biogas digester is the sludge or the slurry. It will be at the bottom. So VSL is the sludge volume, and we know the total volume of the digester will be the sum of all these 4 volumes: V collection, V gas storage, V digestion, and V sludge layer volume. So that is the total volume. We can split the total volume into 4 sections. Then another dimension is based on the geometry, that is, we know the digester mainly we have 3 parts. We can geometrically it have 3 parts. We have a central cylindrical part, as like this in figure, and we have a top and bottom hemispherical part. So that is the geometrical classification, because we will be constructing this biogas digester in 3 parts: the cylindrical portion and top and bottom hemispherical portion. So V1 is the top head volume, that is the hemispherical top part volume. V2 is similarly the bottom hemispherical volume, and V3 is the cylindrical part. Similarly, S1 and S2 are the surface area of top and bottom head, external surface area, and R1 is the diameter of top head, and R2 is the diameter of bottom head, and capital H is the height of cylindrical portion, that is the central portion. Capital H is the height of cylindrical portion. H1 is the height of top portion, that is the hemispherical top part height, and H2 is the height of bottom head, and capital R is the radius of cylindrical part, and D is the diameter of cylindrical part. So these are the geometrical specifications of a digester. So we want to know all these, then only we can construct according to that inputs. Now what are the equations? So mainly we have some equations used for calculation of sizing of a biogas digester. So one is this, that is the V collection. Already we told V collection is the volume where our gas is finally taken outside and collected, and that is should be less than or equal to the total volume. That is one empirical relation, or we have to follow this design equation. V collection must be less than or equal to 5% of V total volume. And similarly VSL, that is sludge layer volume at the bottom, already told at the bottom we have to collect the sludge, and that should be less than or equal to 15% of V. And another important design equation is, if you sum gas storage volume and digestion volume, it should be 0.8 times V or 80%. So that means almost 80% volume, total volume must be given to the gas storage plus digestion. So that is the active volume. So if you consider a digester, the active volume where these mechanisms are happening will be only this volume, VGST plus VD. Other two volumes, that is the V collection volume and V sludge volume, it will not participate in any digestion process. And we have one more equation, that is VGST is also equal to 0.5 into VGST plus VD plus VSL into K. Or we can also use VGST is equal to 0.5 into TS into M. So what are these K, TS and M? K is the gas production rate, how much gas is to be produced per meter cube of the digester volume per day. So it is normally we have to fix that a constant, how much of meter cube of gas is required per day in 1 meter cube. So that is the one constant. Then similarly capital M is the gas production rate per kilogram of total solids per day. So here TS is the total solid content. So how much total, so if you are inputting waste into this, so how much solid content is present. So the waste will be solid plus liquid content in the digester. So in this TS means the total solid content per day. So TS into, so this is also equal to 0.5 into total solid content into M, where M is the gas production rate per kilogram of total. So these two equations are almost same, but here we are in one equation we are representing in terms how much gas required per meter cube. In the other one we are representing it as how much gas required per kilogram of total solid content. So that is the only difference in these two equations. So we can use the first equation itself, that is VGST is 0.5 into VGST plus VD plus VSL into K. So these are the equations, design equations used for finding out collection, V sludge, VGST, etc. Now for geometrical dimensions we have some empirical relations we have to follow. That is, one is capital D must be 1.3078 into V raised to 1 by 3. Then capital V1, that is the volume corresponding to cylindrical part, sorry, this will be 0.0827 into D cube. Then V2 must be 0.05011 into D cube. So these are some empirical relations only. V3 is 0.3142 into D cube. So this is how we have to find out V1, V2 and V3 based on this D. So first we have to determine D based on total volume. Then based on that D, the diameter of cylindrical portion, we have to find all other V1, V2 and V3, etc. And R1 will be the radius of hemispherical top part, 0.725 into D. R2 is 1.0625 into D. Then H1, the height of the top cylindrical part, the hemispherical part is D by 5, and H2 is D by 8. Then surface area S1 is 0.911 into D square, S2 is 0.835 45 into d square. So these are the empirical relations used for finding out R1, R2, H1, H2, etc. the height and diameter, radius, etc. of hemispherical part, other things. Now based on this equation we have to do a simple problem. So determine the volume of the digester chamber and dimension of the chamber for biogas production from cow dung of 10 cows having a body weight of 200 kilogram each. The assumed temperature is 330 degrees Celsius. The solid content of cow dung is 60%. And HRT, the hydraulic residence time, is 40 days. One cow produce 10 kilogram of cow dung daily. So this is a typical problem. So suppose one farmer has 10 cows and each cow is producing approximately 10 kilogram of cow dung daily. So you want to select a digester of particular size. What are the dimensions, etc. of a digester? He want to know. So in this, the body weight of cow, etc. are not have any importance to our problem. This does not matter how much the body weight of cow, etc. So only thing we want to know is how much kilogram of cow dung one cow produce. So here it is 10 kilogram. And another important thing in the problem is the solid content of cow dung. So if you take cow dung, its solid content is 16%. So the remaining 84% will be liquid. And another thing given is the residence time. So residence time means how many days we have to keep this cow dung to convert into biogas. That is 40 days. So these are the given data. So what will be the total discharge per day? So total discharge per day is 10 into 10, 100. So total discharge per day is 10 kilogram into 10, that is 100 kilogram per day. So one cow produce 10 kilogram. That means 10 cow produce 100 kilogram. That is the total discharge per day. Then total solid content of fresh charge. So we know that 16% of cow dung is solid. So if you take this 100 kilogram, in that only 16 kilogram will be the total solid. And another important thing is in biogas digestion, normally we have the concentration of solid content, the optimum concentration should be 8%, not 16%. So we have to add water. So before putting this cow dung into the digester, we have to mix it with water to make it as 8%, because normally in a digester 8% is the most suitable condition, solid content percentage. So we have to add 100 kilogram of liquid or influent. So already we have 100 kilogram of discharge. In that 16 kilogram is solid. So how much we have to add? So total influence should be 200. So to make it 8%, the total content should be 200. So we have to add 100 kilogram. Already 100 kilogram is the discharge produced by the cow. In that we have to add 100 kilogram. So our total discharge is 200, not 100. So that we have to take care of. So here the cow produced 10 kilogram of cow dung. So total discharge is based on that is 100. But in that 16% only the is solid content. So but we want 8% concentration solid content for the digester to operate. So we have to add water or liquid So how much we have to add? We have to add 100 kilogram more. So the final discharge or final input to the digester will be 200 kilogram with the 16 kilogram solid. So that the total percentage will be this much percentage, that is 8%. So that we have to consider. Now we know first we have to start this using the working volume. The working volume of digester is VGST plus VD, that is gas storage volume plus digester volume, and this is the important equation we have to use, that is VGST plus VD is equal to Q into HRT. So total working volume is equal to Q is the total discharge into hydraulic retention time or residence time. So this equation you have to by heart or understand, that is a total working volume. Total working volume will be the sum of gas storage volume plus active digestion volume. That is equal to Q into HRT. Q is total discharge. HRT will be given, that is residence time or retention time is 40 days here. So substituting this, we will get VGST plus VD is equal to 200, that is 200 kilogram is our total discharge into 40 days. So that means total discharge this 8000 kilograms. So the 8000 kilogram we have to handle, that is a total kilogram of discharge in this 40 days. And assuming we know almost the content, most of the content is water, so we can assume the density as 1000. So to handle this 8000 kilogram, how much volume we require is 8 meter cube, because density we have known that density of water is 1000 kilogram per meter cube. So 1000 kilogram of water we have to take 1 meter cube. So that means 8000 kilogram of discharge we have to take 8 meter cube. So that is the volume corresponding to this. And we have also this equation. So we have find out that VGST plus VD is 8 meter cube. And we have also this design equation, that is VGST plus VD is 0.8 times total volume. So what will be V? Total volume will be 8 by 0.8. So VGST plus VD is 8 meter cube divided by 0.8. So total volume, we have find out the total volume for handling this this digestion process is 10 meter cube. Now we can use the design equation, that is geometric equations. First we have to find D. Capital D is the diameter of cylindrical portion. We have to use that equation, that 1.3078 into V raised to 1 by 3. So we are getting, substituting, we will get 2.8176. That is almost equal to 2.82 we can take. Similarly, the other volumes we can find out. V3 we is pi D2 into H by 4, or we can also consider this equation. V3 is pi into D cube. So already we have find out the diameter 2.82 meter. Substituting, we will get V3, so that is 7.046 meter cube. And we all other things we can just substitute equation. For capital H is, we can find out using that corresponding equation, it will be 1.129 meter. Similarly, H1 is D by 5. So substituting, we will get 0.564. H2 is D by 8. So H1 and H2 are height of the hemispherical part, top and bottom part. Just substitute. Similarly, capital R1, the radius of top part 0.725 D. R2 is 1.0625 d. So all these are just substitutions based on the design equations. And V1 0.827 d cube, V2 0.05011 d cube. So all these we can find out. And V collection is, we know that it should be less than or equal to 5% of total volume. So we can take equal to 5% of total volume. 0.05 into V, that will be 0.5 meter cube. So how to find out VGST and VD? So already we find out VGST plus VD, but in that how much is VGST, how much is VD, we have to understand. So for that we can use this equation. VGST is 0.5 into VGST plus VD plus VSL into K. So what is this 3 volumes? If you add these 3 volumes, it will be the same as total volume minus collection volume, because if you add all the 4 volumes, we will get the total volume. So if you subtract total volume minus this collection volume, we will get this VGST plus VD plus VSL. So this is also equal to 0.5 into V minus V collection volume into K. So like this you have to find out. So already we have find out V, that is 10 meter cube. Now this collection volume is 5% of V, so that is 0.5. So if you subtract that, we will get 9.5. And K is the how much gas is required per meter cube of this volume per day. So that will be normally 0.4, maximum 0.3, that's a constant. So here we are taken it as 0.4. That means per 1 meter cube we will get, corresponding to the volume, we have to get the 0.4 of gas, biogas. So substituting, we will get VGST as 1.9 meter cube. So like this we have to find out VGST. So this is the geometrical dimension marked. Already we find out what is V1, the volume of top portion, V2, the volume of bottom portion, then V3 will be the remaining volume. So total volume is 10 meter cube. So if you subtract 10 minus V1 plus V2, we will get V3. And R1, R2 is another important dimension we require. Similarly H1, H2 and capital H. So all these simply we can find out using these design equations. So like this we can select the size of a digester based on our inputs. So we have to do more problems like this from textbook, etc. Now what are the impurities in biogas and their impacts? So we know that biogas is not only methane, it contains carbon monoxide, hydrogen sulfide, siloxanes, that is silicon compounds. So all these will be present in trace amounts, but even if it is present in very small quantity, it affects the application. That is, if you are using biogas in an engine or if you are using it in a turbine, that will affect the components. So let's see how these impurities will affect the applications. So first one is moisture. You know, if the moisture is present, it will result in corrosion of compressors. So the biogas will be compressed in a compressor, so it will result in the corrosion of compressors and engine, because it reacts with hydrogen sulfide, ammonia, etc., carbon dioxide, etc. in the biogas to form acid. So that is, we have to eliminate the moisture also. So if moisture is present, it will act with this other gas, hydrogen sulfide, ammonia, CO2, etc., to produce acids. And it will also result in the accumulation. When it is condensed, it will result in the accumulation of water in pipes. Condensation and freezing, etc. will happen. So all these are the impacts of moisture. And another important impurity is hydrogen sulfide, which is very harmful, which is corrosion. This will result in corrosion in compressors and engines. and if sulfur compounds are present, it will act with this and it will form more toxic acid forms, hydrogen sulfuric acid, etc., sulfurous acid, etc., and it is more damage to the components. So anyway, this hydrogen sulfide we have to remove from biogas if you are using it in compressors and engine, etc. And if dust is present, we know it will result in the clogging of compressor pipes, gas storage tank, engine, etc. So dust also we have to remove. Then another important component is carbon dioxide. We know that carbon dioxide is almost 10 to 20% or more than that will be carbon dioxide in biogas, so that we cannot avoid. But the problem is carbon dioxide is a non-combustible gas and its presence will lower the calorific value of biogas. So if carbon dioxide is present in more amount, the calorific value of that biogas will be very less. So if you are removing carbon dioxide, means you will get a more heating value for that biogas. So that is the importance of carbon dioxide removal. And if oxygen is present, we know that anaerobic digestion is carried out in the absence of oxygen or air. But if somehow this oxygen and air are leaked into this, the chance of explosion also is there, because the biogas is a combustible gas. If it is mixed with oxygen and some temperature increase, etc., is there is a chance of explosion. Then another important impurity that may be present is siloxane. So what is siloxane? It is a silicon compounds. It is present in cosmetic and other consumables. So if you are using municipal solid waste, mainly if you are using municipal solid waste for biogas digestion, this siloxanes will be present because it is already there in this most of the products we are dumping. So that is also very dangerous. They will form silicon oxide, quartz, microcrystallized quartz, etc., due to combustion, and they will deposit in spark plug valves, etc., of engine. So that is very, very dangerous. It will finally, the engine will stop working due to this spark plug damage. And another thing is some higher order hydrocarbons and chlorine, fluorine, etc., will be present. All these are results corrosion of combustion engine. So all these impurities we have to take care. If you are applying this biogas digestion in an engine or turbine, etc., we have to remove these components. So mainly hydrogen sulfide, carbon dioxide, and siloxanes. These three are the major pollutants or the contaminants that must be available in biogas. So we have to remove this before finally applying this in other applications. Now finally, how we are to utilize this biogas. Already we have a biogas, suppose we have a particular quantity of biogas. How to use this? So we have different approaches or different routes are there for the utilization of biogas. So this you can in detail you can read in this particular journal paper, the Advance in Biogas Valorization 2020. It's a review paper. So these are the overall applications of biogas. So mainly we have two applications, direct and indirect. So direct application is the most useful one. So that is for cooking and lighting. So direct heating, we are using biogas in rural areas, India, China, etc., either for direct cooking or for lighting purpose, where electricity and other LPG connection, etc., are not possible. We can use this biogas. So we can produce biogas from the waste from kitchen or hotel, etc., collect that biogas, and we can directly use that for cooking and other heating purpose. But we have other indirect utilization, and indirect utilization we can have physical, chemical and biological classification again. So what is physical classification? In physical classification, we have just clean the biogas. That cleaning means we have to remove carbon dioxide, hydrogen sulfide, siloxane, etc. by suitable method, and directly we can use it for different applications. What are the different applications? After cleaning, we can use biogas for boiler as an input for boiler fuel. We can use it for power production, combined heat and power, CHP. How we can produce power production? We can again classify how we can produce power production. We can use IC engines, particularly petrol engines. We can use micro turbine. So micro turbine is a miniature form of gas turbines which runs in Brayton cycle. We can use Stirling engine, which is an external combustion engine. Fuel cell also, we can use solid oxide fuel cells. So these are some options. Suppose we want to produce electricity from biogas. After cleaning, we can select any of these based on our requirement. Either we can use IC engines, or we can use micro turbines, or we can use fuel cell, or you can use Stirling engine. So all these having some advantages and disadvantages. You can find out reading this review paper more. And another thing is, if you are separating methane completely from biogas, we can use it as natural gas transport fuel. That is, we know that in our Kerala etc. also we are now using compressed natural gas, which is 100% methane. Now if you are removing methane completely from biogas and separate it 100% nearly, we can directly use it for as a transport fuel. And we can all, in some developed countries, grid injection, we can inject this compressed natural gas to the grid of natural gas, CNG pipeline. So that is not possible in this India etc., because biogas will have different composition in different. But in some developed countries like Norway, they have these centralized biogas plants where they will separate methane and convert into natural gas. This is same as natural gas, and they will inject this into grid. And we can also liquefy this biogas. So these are the some options. And also we are getting carbon dioxide. If you are separating methane, means other 20% or 10% we are separate, we will get carbon dioxide. So they can also use the byproduct carbon dioxide. We can also use for heating in greenhouse, in refrigeration. This carbon dioxide is also used as a refrigerant. Then enhanced oil. So these carbon dioxides are used in different industry applications. So all that we can use. Then another possible way is the chemical pathway. What is chemical pathway? So we are converting biogas with the help of some chemical reaction into other products. For example, syngas. So syngas is a mixture of hydrogen and carbon monoxide. So how to produce syngas from this biogas? We have to use steam reforming. So if you add steam to biogas in a particular temperature and reaction taken, and this methane and carbon dioxide is converted to hydrogen and carbon monoxide. So if you want hydrogen from biogas, you can use this steam reforming. Similarly, different reactions, we will get methanol, ammonia, acetic acid, etc. So that is the chemical pathway. So we are chemically converting biogas into different other forms. And another final pathway is the biological pathway. So biological pathway, we can use some other enzymes and other some biological organisms to convert this into some proteins, polymers, etc. So that is only a limited application only. In some special case, we can convert this biogas into some biopolymers, some other polysaccharides, etc. So this is the overall application. So in this, now mainly we are using for biogas for cooking only, cooking and direct heating purpose only. But we can use it for power production and we can use it for transport fuel. So all these research are going on. So if you are interested in this area, you can read this paper and find out what are the applications of this biogas. So with this we are stopping this session. Thank you.